Night spreads like a slow tide across a world that believes itself solid. A stone on a windowsill keeps its quiet shape. A clock divides the dark with measured teeth. Yet under the stone's calm lie fields without form, probabilities braided like mist. Beneath the clock's confidence, time flexes, dilates, and, at the edge of gravity, nearly stops. In the space between breath and breath, reality loosens. A photon chooses a path only when watched. A black hole hides a book and gives back only heat. Equations that fit the cosmos like a glove whisper that space may be woven from information, that geometry is a shadow of entanglement, that what exists is not a thing but a relation. Here, certainty is a costume. The audience, galaxies, atoms, minds, performs on a stage that could be made of bits, qubits, or something older than number. Einstein turns time into a dimension. Quantum theory turns cause into a quiet rumor. Thermodynamics turns order into a debt that must be paid. In laboratories, clocks perched on shelves a few centimeters apart disagree about the rate at which moments happen. In the sky, light from the first fires of the universe arrives carrying tiny wrinkles that seed everything familiar. At the horizon of a black hole, the script is redacted. What then is reality, if not simply the sum of what is seen? Is it the manifold of spacetime, the weave of quantum fields, the grammar of mathematics, the ledger of information, or a tapestry of all of these at once? Tonight, the question is taken seriously, not as a riddle to decorate thought, but as a problem the universe insists upon, with experiments as its punctuation and wonder as its tone. Reality enters the frame as a layered composition. At the front sits the everyday world, tables holding their shape, planets obeying quiet arcs, clocks stepping forward with polite regularity. Beneath that surface, a second layer moves, a pliant geometry where distances and durations depend on motion and mass. Deeper still, a substrate without shape plays host to fields and quanta that refuse to be pinned to definite stories until interactions make them so. Each layer does not cancel the one above it. Each supports, corrects, and sometimes contradicts it, like harmonics in a single note. The central line of inquiry is not whether one layer is real and the others are not, but how these layers interlock, how classical appearance rises from quantum substrates through the scaffolding of relativistic geometry, and how information threads through them all as a hidden grammar. The narrative spine follows the historical path by which what is changed meaning. First a stage for motion, then a dynamical fabric, then a weave of probabilities and correlations, and lately the suspicion that what matters most is neither particles nor points in space, but the relations that bind them. In the 17th century, the stage seemed clear and absolute. Isaac Newton gave the world a stable arena, space and time as independent, universal backdrops, and a law that stitched motion to force with crystalline predictability. The inverse square pull of gravity explained the fall of an apple and the sweep of the moon, suggested a cosmos governed by symmetry and continuity, and granted the imagination a clockwork charm. Initial conditions set, equations applied, futures unfolding like clockwork teeth. Under that vision, reality meant positions and velocities at instants laid out along an immutable time, each instant a page in an already printed book. 2 centuries later, electricity and magnetism, once catalogs of shocks, sparks, and lodestones, found one voice in James Clerk Maxwell's equations. Their solutions revealed waves in the electromagnetic field traveling at a fixed speed. See, this was not merely a detail. It was a warning flare. If the stage were truly absolute, different observers could disagree about the speed of light. Yet the mathematics insisted on a single value, suggesting the stage was not as Newton pictured. The equations whispered that the constant belonged not to any lamp or ether, but to reality itself. Albert Einstein took the whisper seriously. In 1905, special relativity dissolved absolute time into a network of intervals measured along world lines, with simultaneity losing its universal passport. Space and time, once separate ledgers, merged into spacetime, a single manifold whose geometry guaranteed that light's speed stayed invariant. A decade later, general relativity transformed gravity from a force into curvature. Mass and energy told spacetime how to bend. Spacetime told matter how to move. Reality's stage became a restless actor. Observational anchors followed. The anomalous 43 arcseconds per century advance of Mercury's perihelion fell into line. The sun's mass bent starlight, measured during a 1919 eclipse. Redshift in strong fields and high towers shifted the pitch of time itself. A century on, interferometers would listen as black holes collided and spacetime rang, confirming that the fabric is not only curved but elastic, capable of carrying waves across hundreds of millions of light years. Yet while geometry learned to breathe, solidity began to blur. At the turn of the 20th century, Max Planck's desperate trick, quantizing energy, solved blackbody radiation's ultraviolet catastrophe and introduced quanta as more than bookkeeping. Einstein treated light as parcels to explain the photoelectric effect, making energy granular. Niels Bohr's atom set electrons on specific rungs. Then Werner Heisenberg and Erwin Schrödinger gave the atom a more unsettling home. Uncertainty as a principle, the wave function as a predictor of possibilities rather than certainties. Experiments turned metaphor into fact. In 1922, the Stern, Gerlach apparatus split a beam of silver atoms into discrete paths, printing the binary signature of spin onto a plate. The double-slit experiment, whether with light or single electrons, drew interference patterns that dissolved when paths were watched, a choreography in which observation and outcome became inseparable. In 1935, the EPR paper pointed to the strangeness with surgical clarity. If quantum theory's statistics are complete, distant systems could share correlations that seem to outrun locality's leash. The suggestion was not a loophole but a signpost. Across the sky, the universe wrote its own footnotes. In 1929, Edwin Hubble read retreat in the spectra of receding galaxies and declared that space itself expands. Mid-century, a faint hiss leaked into a radio receiver in New Jersey. Arno Penzias and Robert Wilson found the fossil light of the hot early universe, a nearly perfect blackbody bath at a few degrees above absolute zero. Later, spacecraft would map that afterglow, the cosmic microwave background, with exquisite precision. WMAP and Planck revealed tiny temperature ripples at the level of 1 part in 100,000, acoustic fingerprints of primordial sound waves beating through a plasma sea. Those ripples seeded galaxies and clusters, the familiar large-scale web drawn from quantum seeds inflated to cosmic altitudes. The narrative might have settled here, a universe expanding, cooling, assembling structure under gravity's patient hand. Then in 1998, the brightness of distant Type Ia supernovae delivered an unanticipated verdict. The expansion is not slowing, it is accelerating. Whatever fills most of the cosmos acts like a pressure that pushes apart. Dark energy entered the lexicon, and with it, a renewed humility. Reality, so carefully described, now contained a dominant component whose nature eluded description. Against that background, several voices became guideposts. John Archibald Wheeler offered a slogan, "It from bit," suggesting that what exists may arise from acts of distinction, information, rather than material blocks. The phrase was not doctrine but direction, a way of listening for patterns where measurement and meaning meet. Jacob Bekenstein proposed that black holes possess entropy, proportional not to their volume but to the area of the event horizon. Stephen Hawking, quantizing fields in curved spacetime, found that black holes radiate. Together, these insights suggested that horizons store information, and that geometry keeps accounts in units written on surfaces. John Bell, cutting into the EPR knot, proved that any theory preserving local realism must satisfy specific inequalities. Experiments would later violate them, indicating that the world either sacrifices locality, classical realism, or both. In any case, separability, the notion of independent parts with independent properties, could not be the full story. The lineage continued into the present with new bridges across old divides. A duality proposed in the late 1990s showed that certain gravitational theories in a bulk spacetime are equivalent to quantum field theories without gravity on a boundary. Gravity became a hologram for quantum dynamics elsewhere. Quantum dynamics encoded geometry. Entanglement entropy in the boundary theory appeared to measure areas of minimal surfaces in the bulk, the Ryu-Takayanagi prescription, elevating information to a geometric sculptor. Later arguments hinted that stitching together entanglement patterns can assemble patches of spacetime, while cutting them can tear geometry. A conjecture whispered that entanglement and wormholes might be two ways of describing the same connection. In parallel, new tools for calculating particle scattering, the amplituhedron and on-shell methods, hinted that the familiar stage of spacetime and locality may be emergent conveniences, not the engine itself. Other programs, such as loop quantum gravity, proposed that areas and volumes come in discrete quanta, that geometry is woven from spin networks whose combinatorics replace continuum smoothness at the smallest scales. These avenues differ in mathematics and emphasis, but converge on a single mood. The classical world is not the bedrock. It is a fluent translation of deeper structures. Observations and instruments keep the story honest. Atomic clocks perched only centimeters apart tick at different rates, verifying that time's pace answers to gravity's pull even in a laboratory. Interferometers measure spacetime's quiver as black holes merge. Telescope arrays resolve a ring of light around a galactic nucleus, tracing the shadow a black hole carves in radiation near its brink. Surveys map the cosmic web across billions of light years, charting how structure grows against the push of dark energy. Quantum networks distribute entanglement over cities, while loophole-free Bell tests erase escape routes from non-locality. Each device answers to a quiet philosophy. The real is what survives the scrutiny of many viewpoints. In this sense, reality's meaning is the overlap among frames, instruments, and equations, the invariants that persist when methods change. The discovery phase lays down a path with an unromantic honesty. Newton's absolutes built a predictive world, then Maxwell's constant speed of light cracked that world's floorboards. Einstein replaced the floor with a living fabric whose curves stack time on unequal shelves. Quantum theory fractured certainty into distributions and correlations that defy classical separability. The sky, treated as archive, confirmed an origin hot and dense, then surprised with acceleration, demanding an unknown component to dominate the ledger. Black holes, once mathematical curiosities, became thermodynamic systems that count in bits rather than bricks. Information, initially a bookkeeping term in communication theory, rose from metaphor to potential ontology. Throughout, the mystery tightens rather than disperses. The classical realm remains true within its reach. The relativistic realm supplants it at high speed and strong gravity, and the quantum realm underwrites both with a logic that resists naive picturing. The layers coexist. A planet falls along a geodesic, its path calculable by smooth geometry, while its atoms obey a calculus of amplitudes. A photon circles a black hole at the edge of capture, yet its description belongs to fields and quanta, not beads on a track. Reality shows consistency across descriptions precisely because those descriptions are not rivals, they are translations. Where the dictionaries between them are incomplete, paradox appears. Information puzzles at horizons, vacuum energy predictions that overshoot observation by staggering factors, measurements that demand a role for the act of measurement itself. In the present, the spine of the story points toward a synthesis that is less a single equation and more a new idea of what existence means in physics. Geometry may be an emergent bookkeeper for quantum information. Entanglement may be the mortar that holds spacetime's bricks. Complexity may be a clock that measures an interior's growth. Or perhaps the bedrock will instead be combinatorial and discrete, a web of relations whose low-energy shadow is smooth. The possibilities differ, but the discovery line has already redefined what is. It is no longer sufficient to count objects and list their positions in an absolute arena. To say that something is real now means, at minimum, that it carries invariant content across observers and survives the narrowing funnels of experiment, that it sits at the intersection where equation, measurement, and coherence meet. Thus the chapter closes not with an answer, but with a sharpened question. The layers have been revealed: the clockwork, the curvature, the quanta, the code. The next steps will test whether those layers are faces of one structure, whether information and geometry are two readings of the same inscription, and whether reality, stripped to essentials, is a fabric of relations that only occasionally appears as things. The first shock arrives as a quiet subtraction. A universal now, once presumed to cover the world like an even snowfall, melts away under the light of relativity. Two events, separated by distance, trade their order when observed from different states of motion. Simultaneity, once the hinge of cause and effect, becomes a local custom, not a global law. Clocks exposed to motion, or lowered into gravity's grip, carve time at different rates. The world line of each device is a private metronome. Muons created high in the atmosphere live long enough to reach sea level because their internal clocks run slow relative to Earth's frame. Atomic clocks flown around the planet return with histories that disagree by microseconds with those left behind. The result is not only counterintuitive, it is ontological. Time, once the river that carried all things forward together, becomes a braided delta of many tributaries, stitched by the invariant speed of light. The geometry that replaces the lost absolute is exacting and beautiful, yet it imposes a philosophical cost. In the block view forced by relativity's equations, past and future are equally inscribed on the manifold, and the felt flow is not a property of spacetime but of thermodynamic arrows and biological memory within it. The observer's life becomes a path laid down once and for all, and freedom, if it exists, must be reconciled with a world where the map looks complete. This is not an argument against experience, but a tension with it. Meanwhile, gravity's reinterpretation as curvature introduces a second disquiet. The presence of mass and energy reshapes the very units used to measure distance and duration. The yardsticks and clocks are not impartial judges standing outside the scene. They are pliable participants. Reality ceases to be a stage and becomes dramaturgy. Into this pliant geometry, quantum mechanics drops a different kind of vertigo. The wave function assigns amplitudes, not certainties. An electron is not here or there until an interaction marks a fact. Until then, it is described by a spread of possibilities evolving in a perfectly deterministic linear rule. Measurement is the rupture, the rule that carries waves forward. The Schrödinger equation delivers outcomes only as probabilities. In practice, decoherence explains why macroscopic experience is stable. Environments entangle with systems, suppressing interference between alternatives and yielding robust, classical-looking records. But the core puzzle remains. The formalism treats all evolutions as unitary entanglement, yet outcomes appear definite. The measurement problem is not a technical glitch, it is an ontological fork. Either the world branches, or probabilities reflect subjective betting odds tied to agents, or collapse is a genuine dynamical process that remains to be found. The double-slit experiment exposes the fracture line like a fault running under a city. With both slits open and the path unobserved, even single quanta accumulate an interference pattern that no classical particle picture can muster. Insert a witch path detector, and the pattern vanishes, replaced by two classical-looking humps. Correlations have been rerouted. The lesson is merciless. Reality's appearance depends on the web of relations linking system, apparatus, and environment. There is no picture of what the electron really did that simultaneously preserves locality, separability, and the observed statistics. Heisenberg's uncertainty is not a story about clumsy instruments. It is a statement about the structure of propositions that can be true at once. Questions that can be asked together are constrained by the algebra of observables. The shock is not that nature hides information from nosy observers, but but that certain information does not exist as a consistent assignment prior to the acts that create it. Bell's theorem hardens suspicion into proof. Any worldview preserving both locality and a classical notion of realism must satisfy inequalities that quantum theory violates. The experiments, refined across decades to close detection, locality, and freedom of choice loopholes, agree with quantum predictions. The options narrow. One may keep realism and sacrifice locality, building non-local hidden variable accounts with superluminal coordination. One may keep locality and adopt a softer realism, treating the wave function as an instrument that encodes expectations for experiences rather than properties possessed by systems independent of context. Or one may accept an ontology of branching worlds, where measurement simply reveals which branch contains a given observer's record. None of these paths preserves the comfortable image of small objects clustered in absolute space, each carrying definite properties waiting to be read. The world seems to consist fundamentally of correlations, patterns of joint possibility, rather than separable stuff. Where quantum strangeness meets gravity, the ground tilts again. Black holes born when mass collapses past the point of no return appear to seal information behind a horizon. Bekenstein's insight, that horizon area measures entropy, binds geometry to bookkeeping. Hawking's calculation grants black holes a temperature, and therefore radiation. If the evaporation proceeds to completion, the final state looks thermal, apparently uncorrelated with what fell in. Unitarity, the demand that quantum evolution preserves information, seems violated. The information paradox is not a taste for metaphysics. It is a precise conflict among three principles long believed to be cornerstones: quantum mechanics, unitarity, general relativity's causal structure, and the equivalence principle that promises nothing special at the horizon for an infalling observer. Giving up anyone comes at a cost. Sacrifice unitarity and quantum theory breaks. Sacrifice smooth horizons, and firewalls or other radical departures erupt where general relativity promises tranquility. Sacrifice locality, and the horizon must share data with the exterior in ways classical geometry forbids. The paradox is a siren. Reality's current grammar is incomplete. Cosmology adds a dissonant chord. Quantum field theory applied to the vacuum predicts a huge energy density from zero-point fluctuations. Gravity listens to all forms of energy, so the vacuum should curve spacetime ferociously. Observations, however, reveal a cosmological constant, or dark energy density, smaller by about 120 orders of magnitude than naive estimates. This mismatch is sometimes called the worst prediction in physics. It is more than embarrassment. It is a sign that combining quantum fields with classical spacetime misses a cancellation, symmetry, or selection principle. The discovery that the universe's expansion accelerates transforms the mismatch into a measured fact. Whatever dark energy is, constant, field, or modification of gravity, it occupies most of the cosmic energy budget while remaining opaque to direct explanation. Reality's dominant term is the least understood. Even outside the cosmic headline numbers, the scriptures of physics acquire marginal notes that refuse to be erased. The problem of time in quantum gravity asks how to define evolution when the theory's most natural constraints eliminate time as an external parameter. The Wheeler-DeWitt equation looks timeless, yet experience recites a chant of before and after. Entropy's arrow points from uniform beginnings toward structured futures, but the remarkably low entropy of the early universe is a boundary condition not yet explained, only recorded. If the block universe is the arena, the arrow requires a special slice near the beginning with uncommon smoothness. Reality thus seems to include not only laws but an improbable initial condition, or else a deeper rule that makes such a beginning typical within a larger ensemble. In the laboratory, quantum theory's completeness invites a last unease. As systems scale upward, the border between quantum and classical remains a matter of practice rather than principle. Interference has been observed with large molecules and superconducting circuits, macroscopic superpositions are manufactured and stabilized for brief, careful lives. Collapse models propose objective mechanisms that suppress superpositions of sufficiently massive systems, predicting faint, testable deviations from standard quantum behavior. If such deviations appear, reality would include a new stochastic ingredient. If they do not, the pressure grows to accept that definiteness is perspectival, tied to records and contexts, not to a global cut in the wave function. Neither option supports the simple picture of an observer-independent catalog of properties unfolding in time against a fixed background. The shocks taken together are a map of what must be reconciled. Relativity dethrones universal time and freezes the flow into geometry. Quantum mechanics dethrones determinism at the level of outcomes and replaces objects with correlations that defy locality in a classical sense. Black holes dethrone the innocence of horizons, demanding that geometry, information, and quantum theory meet on equal terms. The accelerating universe dethrones a tidy energy budget and forces a new actor, dark energy, onto center stage. Each dethronement subtracts a comfortable intuition and adds a constraint future theories must obey. Any deeper account of reality must produce the everyday world as an emergent summary while preserving the statistical structure of quantum experiments, the causal structure of relativity at accessible scales, and the measured expansion history of the cosmos. Language strains under the load. Words such as particle, field, spacetime, and measurement are not discarded, but they acquire a footnote. Definitions depend on scale, context, and the observer's participation. In particle physics, the vacuum is not empty, but a medium whose excitations depend on the decomposition chosen by an observer's motion and horizon. In curved spacetimes, even the notion of a particle becomes frame-dependent. What is real, then, begins to shift from objects to invariants, quantities all observers agree upon, symmetries that protect laws from parochial frames, entropies and entanglement measures that count relational structure rather than substance. Reality's shock is not that the world is illusory, but that the furniture of the classical imagination is a reliable interface, not the code. Speculation gathers at the edges where equations falter. Perhaps spacetime is not fundamental but woven from entanglement, with geometry an emergent ledger of quantum information. Perhaps locality is a derived convenience, and the true wiring diagram resembles a network where proximity in information space replaces proximity in coordinate space. Perhaps the cosmological constant is small because the gravitational sector averages over vacua in a way that cancels most fluctuations, or because regions capable of hosting observers typically find themselves where acceleration has a particular value, the anthropic strategy within a larger landscape. These are not declarations, but sketches of where the shocks point. Each accepts the experimental facts, respects the symmetries, and seeks an economy of explanation capable of restoring coherence without resurrecting absolutes that data have denied. The enduring shock is not merely that reality is more subtle than first pictures allowed. It is that the successes of physics, its precise predictions, confirmed to many decimal places, coexist with paradoxes that cut to the bone, the status of time, the fate of information, the scale of vacuum energy, the ontology of the wave function. The theories work, and yet their marriage remains unconsummated. Between them stretches a gap that looks less like a flaw and more like a clue. The world remains legible, but the grammar has yet to be unified. The next movements will test whether geometry can be derived from information, whether black holes are mirrors rather than shredders, whether the arrow of time can be rooted in typicality or dynamics, and whether the vacuum's energy can be made to listen to reason. Until then, scientific shock is not disarray. It is a disciplined astonishment, the posture a field adopts when its maps succeed and contradict one another at once. Inquiry pivots from shock to measurement. The question hardens: if reality is layered, classical appearances seated on relativistic geometry, both leaning on quantum substrates, What traces does the layering leave in instruments that refuse to lie? Time is tested first, because it leaves the faintest fingerprints and the most unforgiving arithmetic. In quiet laboratories, optical lattice clocks entrap thousands of neutral atoms in standing waves of light. Single-ion clocks isolate a lone ion in an electromagnetic cradle. Their resonances are knives honed against the edges of uncertainty. At fractional stabilities near 1 part in 1018, a clock can sense a difference in gravitational potential across a human height, raise it a few centimeters, and time changes its pace. This is not romance but record. Networks of such clocks compare notes through fibers and free space links, mapping the geopotential as if it were weather. Time ceases to be a backdrop. It becomes a field to be surveyed, one tick against another, until the field reveals the truth already encoded in relativity. Every place carries its own tempo. Reality does not own a master metronome. It orchestrates a choir of local ones whose harmony is the invariant. Closer to the quantum seam, experiments untie old knots and braid new ones. Loophole-free tests of Bell inequalities place entangled systems in carefully separated stations, coordinating settings with cosmic or fast random seeds, and closing the detection and locality escapes that once offered comfort. Results land where theory predicted. The statistics resist any description that keeps both locality and a classical realism intact. The world records correlations that cannot be manufactured by stories assigning pre-existing properties to each part. Along other tracks, delayed choice and quantum eraser experiments refine the lesson. Choices made late in an apparatus flow backward through the accounting, not to change the past, but to revise which questions were meaningfully asked. The algebra of measurement reorders what could have and did mean, and the laws do not blink. Entanglement travels farther. Photon pairs are separated by mountains and sea, their polarizations measured across long fibers or open air. Quantum teleportation reconstructs states at distant stations through the alchemy of joint measurements and classical relay. A satellite passes overhead, distributing entanglement between ground sites divided by continents, its orbit sewing a fragile thread through the atmosphere. None of this changes the speed limit of signals. No message outruns light. Yet the non-local structure of joint outcomes is no longer a theoretical stanza. It is an engineering resource with a pulse and a logbook. Reality's fabric permits correlations that space alone cannot explain, and instruments now wear those correlations like medals. Where gravity grows loud, telescopes and interferometers report on geometry's moods. Laser interferometers hewn from vacuum tubes 4 kilometers long await the lightest shiver of spacetime. When black holes collide, the apparatus hears it. Each detection sketches a story. Masses and spins, distances and angles, a waveform's rise and ringtone tracing equations derived a century ago. The signal is not only a discovery, it is a calibration. The consistency of many mergers allows tests of strong field general relativity, hunts for deviations in ringtone notes, searches for dispersion that might hint at a graviton with mass. Thus far, the equations hold, but their survival in a regime of violent curvature exposes the remaining gap more starkly. Quantum theory reigns in the small, relativity in the large. Both refuse corruption in their proper courts. The difficulty lies in the corridor between them. The eye turns to horizons. A planet-sized array of radio dishes, synchronized by atomic clocks, stares at galactic centers and resolves, at last, the silhouettes of black holes. A bright ring appears where photons orbit precariously. A dark interior marks the capture of light. The diameter of the shadow, the asymmetry of brightness, the pattern of polarized emission, all speak a dialect of curved spacetime and magnetized plasma. Models of accretion translate the image into a census of flows and fields. Comparisons test whether the shadow size tracks the mass as general relativity commands. The early verdicts favor curvature's script, but even this fidelity sharpens the open question. The event horizon, outwardly faithful to general relativity, must also be a ledger for quantum information if unitarity is to survive. The photograph does not answer. It intensifies the demand that any reconciliation preserve both the classical exterior and the quantum bookkeeper within. Above the horizon, the universe remains a fossil bed. The cosmic microwave background carries anisotropies at the level of tens of microkelvin, and satellites have mapped them with exquisite care. Angular power spectra display a series of acoustic peaks and troughs, the frozen harmonics of primordial sound waves in a hot plasma, each peak's height and position encoding densities of baryons, dark matter, and radiation, as well as the curvature of space. Weak lensing of the background by intervening structure smears and curls the pattern, yielding measurements of mass distributions that tie the infant universe to its adult web. Baryon acoustic oscillations, imprinted in the positions of galaxies like a standard ruler, calibrate cosmic distances. Redshift space distortions track the growth rate of structure under gravity's pull. Each survey adds a layer to the ledger. Maps of the large-scale web, measurements of the Hubble parameter across epochs, constraints on neutrino masses that weigh ghostly particles through their grip on clustering. The data form a chorus that sings a single refrain in different keys. An expanding universe governed by general relativity on large scales and by cold, nearly collisionless dark matter, with a dark energy component acting like a cosmological constant within current error bars. Yet even an orderly chorus carries dissonances. Independent measures of the present expansion rate do not agree. Local distance ladders using Cepheids and supernovae yield values that sit above inferences from the early universe, derived by fitting cosmic microwave background data under the standard model. The gap resists the usual pleas of systematics. Other tensions flicker at the margins. Measurements of structure growth slightly below predictions, large-angle anomalies in the background sky of uncertain significance. None is a verdict against the overarching model. Each is a suggestion that the model's simplicity may hide additional texture, or that the procedures bridging early and late need refinement. Reality offers resistance where precision grows, not as obstruction, but as invitation. In a quieter province, entropy and geometry exchange letters. The entanglement entropy of a region in a quantum field theory tends to scale with the area of its boundary rather than the volume of its interior, an echo of black hole thermodynamics where horizon area measures informational capacity. In certain dualities, the entropy of entanglement in a boundary theory computes the area of a minimal surface in a higher dimensional gravitational bulk. These correspondences are not metaphors. They are equations obeyed by specific theories with sharp definitions. They invite a radical reading. Perhaps geometry is a summary of entanglement patterns, and Einstein's equations arise as constraints that keep those patterns consistent. Toy models build discrete networks, tensor webs in which the geometry of connections dictates how information flows, and show how error-correcting properties can stabilize a code against local loss, much as a spacetime seems insensitive to small perturbations in its microscopic substrate. A dictionary is being drafted in which distance means difficulty of decoding, and volume whispers computational complexity. The manuscript is incomplete, but the section headings grow bolder. Other paths pursue discreteness directly. Programs that quantize geometry itself assign spectra to area and volume, allowing states of space to be listed like notes in a scale. Dynamics in these pictures replace smooth evolution with combinatorial moves. Spinfoams trace histories of how quanta of geometry glue and reconfigure. The challenge is twofold: to recover the familiar continuum at large scales, and to extract smoking gun predictions at small ones where measurements are fiercest. Meanwhile, methods that sidestep spacetime altogether study scattering amplitudes using on-shell principles, discovering polytopes whose volumes encode probabilities that particles exchange momenta. The algebra suggests that locality and unitarity may be emergent from geometric consistency rather than axioms. No single line dominates. Together they sketch, a landscape where the solid stage of classical intuition is replaced by interlocking accounts that succeed where they overlap. Laboratories build smaller worlds to ask safer questions. Ultra-cold atoms arranged in optical lattices emulate Hamiltonians that theorists write on chalkboards but cannot solve. Rydberg arrays simulate spin models whose excitations behave like dimer coverings or constrained gases. Trapped ions mimic fields and gauge couplings. In one class of experiments, analog horizons are constructed in fluids or Bose, Einstein condensates. Excitations near the horizon behave in ways that bear the signature of Hawking's logic, though the systems are not gravity. These are rehearsals, not the performance. They do not decide the fate of black hole information, but they teach how quantum many-body systems encode, scramble, and release information, how correlations spread, how entanglement grows and saturates. They refine intuition and test theorems about thermalization and chaos that any candidate theory of quantum spacetime must respect. Between the cosmic and the microscopic, matter itself continues to confess. Neutrinos oscillate between flavors as they travel, proving they carry mass. Reactors and accelerators map the mixing angles and mass-square differences. Cosmological data limit the sum of the neutrino masses, since heavier neutrinos suppress small-scale structure. Precision tests of the equivalence principle remain loyal to general relativity, placing upper bounds on composition-dependent accelerations that could have signaled new fields. Atomic interferometers and resonant mass detectors search for ultralight dark matter that would make fundamental constants tremble ever so slightly. Gamma-ray bursts arriving from cosmological distances test Lorentz invariance to absurd precision by refusing to disperse. Each null result is a tightening of the net. Each rare detection adds a bead to the wire and forces a rebalancing of what is must mean. Patterns emerge from the total. The classical picture holds where decoherence and coarse graining hide the quantum filigree. Relativity governs the weave of causality and curvature. Quantum theory dictates the combinatorics of possibility. But the lines between them are not seams in a finished garment. They are boundaries where the tailoring is still visible. The deeper layers announce themselves not by defiance but by constraint. Any program that wants to name the bedrock must explain why entanglement obeys area laws in so many contexts, why information and geometry trade currencies at horizons, why complexity behaves like a volume for purposes of growth. It must also preserve, not merely approximate, the experiments that have already survived, the sharp ticks of optical clocks, the delicate violations of Bell bounds, the ring of gravitational waves, the glow of ancient light, the incremental proof that the universe now accelerates. Instruments accumulate facts like silt in a delta, channeling the river into new courses. The accumulation does more than comfort. It produces an aesthetic, the sense that the simplest description of reality is not the oldest, but the one that treats symmetries and invariants as the most solid bricks, that counts relations before objects, that assigns primacy to what cannot be erased by a change of frame. Every tool added to the bench, every clock, interferometer, telescope, trap tests whether that aesthetic is delusion or discovery. Thus far, the tests strengthen the thought that the layers are not rivals. They are translations, consistent where they overlap, suggestive where they do not. Deeper investigation, therefore, does not so much multiply mysteries as refine one. A single question is asked by many instruments. What structure underwrites the success of quantum fields and curved spacetime? And why does information behave like a conserved charge in their courtship? The data offered by clocks and photons, by rings of radio light and ripples in interferometers, by maps of galaxies and entropies of regions, stake out the non-negotiable borders. Any honest answer must live inside them. Beyond the borders stretches a country not yet named, where geometry may be born from entanglement, where time may be bookkeeping for change rather than its cause, where the inventory of the real is a catalog of invariants rather than a census of things. The instruments keep writing in their ledgers. The pattern is there, legible enough to promise that a grammar exists, still faint enough that no sentence has yet been completed. What began as a layered portrait of the world now folds inward, as if the canvas itself were woven from threads more primary than space and more elemental than matter. The suspicion gathers weight. Spacetime may not be fundamental. It may be a fluent summary of something else. Entanglement first, geometry second. So that distance is not an input but a consequence, and curvature is how information organizes itself when viewed at scale. Toy universes speak first. In tensor network constructions, arrays of simple quantum building blocks are stitched into webs that coarse-grain information in stages. The resulting diagrams resemble lattices climbing outward like inverted trees. In these models, neighboring nodes in the network transmit correlations that mimic proximity in a curved space. Cut enough bonds across a surface, and the cut area controls how much information can pass, an echo of area laws for entanglement. When such networks are drawn to imitate a negatively curved space, they sketch a parable. Geometry can be read off from how information is shared. The moral does not stay confined to toys. In holographic dualities linking certain quantum field theories without gravity to gravitational theories in higher dimensions, the entanglement entropy of a region on the boundary is calculated by the area of a minimal surface stretching into the bulk. Equations that once described horizons now govern ordinary partitions of a quantum state. The ledger of information writes the metric. Hints accumulate that reconstruction may run both ways. Knowledge of boundary data, carefully chosen, can rebuild bulk regions. Quantum error-correcting properties protect that reconstruction against local loss, suggesting that stability of spacetime is a redundancy in how information is stored. The idea that connectivity in geometry equals entanglement in quantum theory tightens into a conjecture. Perhaps wormholes and entangled pairs are two faces of the same relation, a statement that two distant subsystems connected by strong correlations are, in a gravitational language, joined by a non-traversable bridge. The bridge cannot transmit signals. It does not cheat causality. But it marks a bookkeeping identity. The stuff of geometry and the pattern of quantum correlations may be interchangeable descriptions across a dictionary not yet complete. Black holes continue to serve as examiners. Their paradox, unitarity in conflict with smooth horizons and locality, has not been filed away. It has been reframed. Calculations of entropy flow during evaporation once produced a curve that rose and never fell, a signature that information was lost. Newer techniques in semi-classical gravity, sensitive to quantum extremal surfaces and replica saddles in path integrals, alter that accounting. The entropy initially grows as radiation accumulates, then bends downward, tracing a page curve compatible with unitary evolution. The mathematics suggests that portions of the black hole interior are encoded non-locally in the radiation outside, once enough of that radiation is collected. These developments do not finalize the microscopic mechanics. They do, however, move the conflict to a sharper frontier. If unitarity survives, then the neat division between interior and exterior enforced by classical geometry is a facade. The price of consistency is that the ledger of where information is depends on which ledger is being kept. Time itself becomes suspect, not in the sense of unreality, but in the sense of demotion from sovereign to subordinate. In canonical attempts to quantize gravity, the equation that replaces the familiar generators of motion is timeless. The constraint that defines physical states does not single out a parameter to label change. Dynamics must be recovered relationally. One subsystem can serve as a clock for another, and correlations between their readings become the record of evolution. Entropy re-enters here as guide and witness. The arrow observed in memory and decay, in mixing gases and burning stars, aligns with a low entropy past whose origin remains a boundary condition without derivation. The universe's early smoothness, so smooth that a few free parameters at recombination tell most of the later story, acts like a hidden instruction. Build complexity from simplicity, grow structure from a remarkably clean slate. Whether inflationary expansion explains that slate by stretching quantum fluctuations into seeds while flattening curvature, or whether a deeper rule makes such beginnings typical in a larger ensemble, remains a live question. Equations supply mechanisms, data supply constraints. The arrow remains a signature of improbability, and therefore a challenge to any proposal that would reduce becoming to mere perspective. When cosmology extends to a grander canvas, another depth opens. If conditions that spark inflation persist somewhere, inflation does not end everywhere. Pockets stop and cool to form island universes with differing details. Elsewhere, expansion continues, spawning new pockets. The overall structure resembles a foam that never finishes forming. Probabilities, once derived from ratios of volumes or counts of events, become ambiguous in a setting that never stops producing space and occurrences. Cutoffs change the answers. Measures compete. Paradoxes arise in which typical observers would appear at times and places unlike those actually recorded. The specter of observers conjured from rare fluctuations, the so-called Boltzmann brains, serves as a warning about naive counting. The multiverse, if it exists, may be real. The current rules for reckoning inside it may be inadequate. Typicality becomes physics' least comfortable word. A different instability haunts the ledger of fields. Extrapolations of parameters measured in colliders suggest that the potential energy governing the known scalar field could render the present vacuum metastable on cosmic timescales. If that is so, then quantum tunneling could, in principle, trigger a phase transition, nucleating a bubble of lower energy vacuum that expands at near light speed, rewriting local laws as it passes. Current estimates, anchored in the measured couplings, make such events fantastically unlikely on human timescales. The possibility lingers as a conceptual thorn. False vacuum decay is not a prediction of apocalypse, but a demonstration that what is may not be protected by logic. It is guarded by parameters whose values stand as facts physics explains indirectly, if at all. The comfort drawn from stability must be earned. At the edge of measurability, practical and principled limits meet. Thought experiments that combine quantum uncertainty with gravitational collapse yield scales at which the very notion of where and when dissolves into operational statements. Attempting to localize an event too sharply means compressing enough energy into a region that the region's description succumbs to its own gravity. The Planck length and Planck time enter not as sacred constants, but as coordinates in a map of failure. Below these scales, standard ways of asking and answering questions undermine themselves. Proposals for generalized uncertainty relations, minimal lengths, and discrete spectra of geometric operators sketch ways in which nature might prevent paradox while leaving familiar physics intact at larger scales. Experimental searches reach toward these thresholds indirectly, by hunting deviations in dispersion near extreme energies, by monitoring interference with massive objects, by listening for Planckian noise. Thus far, nature is tight-lipped. Null results lift lower limits and carve out models. Positive evidence remains an ambition. Even without touching those scales, quantum theory itself complicates what measurability means. Observables are not free-floating propositions. They are tied to reference frames that can themselves be quantum. Changing frames becomes a transformation among quantum systems, not a classical relabeling. The sharp division between system and observer blurs into a hierarchy of agencies, each with consistent records relative to itself, all tied together by consistency conditions rather than a single God's eye account. In that picture, reality is not a monolith of facts, but a tapestry of compatible stories that agree where they overlap and decline to speak where they do not. The demand that a single description cover all frames is replaced by the demand that contradictions never arise when frames meet and compare notes. Consistency, not absoluteness, becomes the law. Complexity, once the concern of computer science and combinatorics, steals a role in this deepening. In certain gravitational dualities, the interior volume of a wormhole, or an action evaluated over a bulk region, tracks a measure of computational difficulty on the boundary theory, growing long past the time when entanglement entropy saturates. The growth resembles a second arrow, pointing toward states that are increasingly hard to reach from simple beginnings. The picture is unfinished and the definitions are contested, but the metaphor has become a calculation. Interior growth in a black hole may be the geometric avatar of rising complexity in the quantum state that describes it. If true, even as a limited correspondence, the statement widens the bridge between information and geometry. Not only entanglement, but the hard work of preparing states would then have a geometric dual. Elsewhere, methods that compute scattering without drawing trajectories trade fields in spacetime for polytopes in abstract space, whose facets encode consistency conditions. Probabilities emerge from volumes and orientations. Locality and unitarity are not postulates, but properties that arise because the geometric object exists. If these approaches generalize beyond the special cases where they shine, they would suggest that even the most elementary predictions of particle physics can be derived without reference to an underlying spacetime. The familiar arena would then be a reconstructed convenience, powerful yet derivative, much as thermodynamic temperature is real and measurable but secondary to microstates. Dissonances in data, minor in amplitude but persistent in character, reinforce the sense that the map must be enlarged. Measurements of the present expansion rate disagree depending on whether the ruler is built from early universe physics or from nearby candles and yardsticks. The growth of structure, when tallied, leans a touch below the value extrapolated from the pristine sky. The oldest light, when sifted for alignments and anomalies, shows low significance hints that prompt arguments rather than conclusions. Each tension may vanish under better calibration. If any survive, they will demand adjustments at the interface between gravity and the ingredients that fill space, or in the initial conditions smoothed and set in the first instance. Reality's surface is smooth to the eye. Under magnification, the grain becomes visible. The escalation, then, is not a multiplication of mysteries but the tightening of a few. Spacetime status slides from given to emergent. Information status slides from accessory to central. Time status slides from river to relation. Horizons, once boundaries, become instruments whose areas count what can be known. Interiors, once hidden, become dual to complexities outside. Cosmology, once a history of cooling and clumping, becomes a debate over measures, typicality, and beginnings. Quantum theory, once a manual for predictions, becomes an ontology of correlations that may hold the blueprint for the stage itself. Each slide preserves what works, the precision of clocks, the strength of gravitational waves testimony, the liturgy of spectral lines, while moving the conceptual weight beneath them. What deepens most is the criterion for reality. In earlier eras, the real was what could be touched or seen. Later, what could be measured. Later still, what remained invariant across changes of frame. The emerging criterion adds a further clause. The real is what is necessary for the mutual consistency of all accurate descriptions. If geometry is needed because entanglement patterns cannot otherwise be consistently summarized, geometry is real, even if emergent. If entanglement and error correction are needed because geometry cannot carry information without redundancy, then information is real, even if relational. The stage and the script become each other's reasons. From this vantage, the open questions sharpen rather than multiply. What microscopic degrees of freedom underwrite the smooth manifold of spacetime, and how do their entanglement patterns produce curvature at low energies? How do horizons record and release information without allowing superluminal signals or tearing infalling observers? What boundary conditions or dynamics set the universe's low entropy beginning and determine whether acceleration is a property of empty space or a field that evolves? Where does time come from in theories whose natural statements are timeless? And why do arrows align across thermodynamics, complexity, and memory? And if the known vacuum is metastable, what protects the present chapter long enough for questions to matter? Instruments will not answer alone, neither will pen and paper audacity. The path forward asks for both: calculations that respect every successful decimal place and experiments that squeeze new ones from reluctant systems. What deepens is the demand for unity without violence. No abandonment of quantum mechanics, no betrayal of relativity, no disdain for data. The escalation is a refinement of taste. The expectation that the final grammar will make the everyday robust, the astronomical grand, and the microscopic strange, while showing that these are not different worlds but different translations of one. Speculation follows evidence the way tide follows the moon, pulled, patterned, never free to choose its shoreline. The layered portrait has set its boundaries. Relativity holds in the realm of curvature, quantum theory governs the combinatorics of possibility, and observation binds them with a ledger of facts that refuses revision. Within those borders, the question sharpens. What exactly is the ontology that makes the layers fit? What does real denote when particles are excitations, spacetime is elastic, and information keeps the better books? One family of answers begins not with gravity but with the wave function. Interpretation is often mistaken for commentary. Here it is architecture. In Copenhagen-style pragmatism, the wave function is a tool for predicting statistics of outcomes, and collapse is the bookkeeping name for the update upon acquiring a fact. Reality, in this view, inherits a modesty clause. What exists are outcomes stabilized by records and the apparatus that produced them. Decoherence gives that clause teeth. Environmental entanglement suppresses interference between alternatives, making robust histories that look classical inside their own webs of correlations. A different stance, the Everett or many worlds picture, treats the wave function as ontic, with unitary evolution never interrupted. Measurement produces branches, each harboring a definite record. Probabilities are weights on these branches rather than dice cast by nature. A third approach, cubist or participatory, moves reality toward personalist probability. Quantum states encode expectations relative to an agent's experiences, and the consistency rules of quantum theory constrain those expectations. Objective collapse models, by contrast, add dynamics. Wave functions undergo spontaneous, rare, mass-amplified collapses, GRWCSL, yielding definite outcomes without observers and predicting faint deviations from standard quantum mechanics that experiments continue to chase. Penrose-style arguments hint that gravity itself might trigger collapse, tying definiteness to spacetime structure. None of these choices alters the laboratory ledger thus far. Each writes a different ontology behind the same statistics. The price of clarity in one direction is metaphysical weight in another. The conversation changes key when gravity is invited. String theory makes the boldest proposal. Replace point particles with extended objects whose vibrational modes give rise to the particle spectrum. Embed them in a framework dense with symmetry and duality, and let consistency dictate dimensions and interactions. In this arena, gravity is not added, it is inevitable. Quantum gravity appears as part of the same fabric that hosts gauge forces and matter. Out of this fabric, a more radical idea emerges: holography. In certain spacetimes, especially those with negative curvature, a gravitational theory in the bulk is exactly dual to a quantum field theory on its boundary, one dimension fewer and with no gravity at all. Reality, in this telling, tolerates more than one perfect description. Geometry and quantum fields can be different dialects of a single poem. The Ryu-Takayanagi relation pushes the audacity further. The entanglement entropy of a region on the boundary equals the area of a minimal surface in the bulk. Information sculpts area, correlations draft geometry. Loop quantum gravity begins elsewhere. Quantized geometry itself. Areas and volumes acquire discrete spectra. Spin networks replace smooth continua at the smallest scales. Spin foams record histories of how quanta of geometry glue and rearrange. The manifold of everyday experience would then be an emergent average, the way a fluid's smoothness hides molecules. The program's restraint is its wager. It changes less of the known world and insists that the continuum is not required to be fundamental. The challenge is equal and opposite, showing how classical spacetime, with Einstein's equations intact, flows out of the underlying graph, isolating predictions that distinguish loops from strings where instruments can reach. A third road abandons substance for relation. It from qubit treats entanglement as primordial in geometry as a bookkeeping device for the pattern of correlations. Tensor network toy models, drawn like inverted trees or stitched carpets, demonstrate how area laws arise naturally and how cutting bonds across a surface limits the information that can pass. In holographic settings, quantum error correction appears not as metaphor but as machinery. Bulk information can be reconstructed from many overlapping boundary regions, and small losses do not destroy the whole. Spacetime is resilient because information is redundantly stored. ER equals EPR compresses a new identification into a symbol, a wormhole, an Einstein-Rosen bridge, and a pair of maximally entangled qubits, Einstein, Podolsky, Rosen may be two views of the same connection. The bridge is not a tunnel for signals. It is a correspondence between connectedness in geometry and connectedness in information. If these threads hold under pressure, then distance becomes derived, curvature a census of correlation, and horizons are not secrets but surfaces on which counting is done. Scattering theory adds a geometric riddle of its own. Traditional calculations employ fields defined at every point in spacetime, then suffer under the complexity of virtual detours. On-shell methods change the question. Compute only with physical mass-shell data and let consistency, unitarity, and locality emerge as consequences of a higher simplicity. The amplituhedron, a polytope in an abstract space, produces scattering amplitudes as volumes. Its facets encode constraints that would otherwise be imposed by hand. If this program generalizes, then even the most basic predictions of particle physics may not require spacetime as scaffolding. Locality and unitarity would be shadows cast by convex geometry in a space of kinematic variables. Spacetime would remain as a phenomenally precise interface, but might not staff the engine room. Dark energy keeps theory moored to data. The simplest fit, Einstein's cosmological constant, survives scrutiny, a constant energy density that dilutes neither with expansion nor with time. Yet quantum field theory's naive estimate for vacuum energy overshoots the measured value by an absurd gulf. Alternatives arise. Quintessence fields rolling slowly down shallow potentials, whose pressure propels acceleration, and whose dynamics might leave subtle imprints in the expansion history, or in the growth of structure. Modified gravity frameworks that alter the relation between mass and motion on cosmic scales, while evading the iron grip of solar system tests via screening mechanisms. Massive gravity and scalar, tensor theories that flirt with new degrees of freedom and face the discipline of gravitational wave propagation speeds and lensing maps. Each proposal must preserve the exquisite successes of general relativity and the standard cosmological model while tamming the constant's embarrassment. At present, the constant does not yield. Rival ideas spend their courage and return with constraints. The mystery shows patience. Speculation touches the status of mathematics itself. Structural realism claims that relations, the symmetries, invariants, and morphisms that survive across frames, are the proper occupants of reality, while objects are placeholders in those relations. The so-called mathematical universe hypothesis goes further. Physical existence and mathematical existence coincide, and the universe is not described by mathematics. It is mathematics. This is not an argument about numbers living in Platonic vaults. It is a claim about identity, that the structure sufficient to generate all observations is identical with the structure itself. The caution remains that physics earns its keep by contact with measurement. Any metaphysics must reduce to rules that pick out the same invariance experiments bless. Even so, the structural lens clarifies why dualities do not insult reality. Two theories can be literally the same structure in different dress. The simulation argument arrives like a mirror in a dark room, reflecting more than it reveals. If minds and worlds can be simulated with fidelity inside computational substrates, and if civilizations that can do so choose to, then statistics might favor existence inside such a simulation. For physics, the value of this thought is not its ultimatum but its discipline. It encourages searches for lattice artifacts at high energies or for breakdowns of symmetries that a finite computation could not sustain. It urges humility about substrate and interface. It reminds that computation is not merely metaphor but methodology. Nature often behaves like a processor, optimizing paths, saturating bounds, trading entropy for work. Yet absent distinctive, testable signatures, the simulation idea is best treated as a fence at the edge of metaphysics, useful for packing, dangerous to vault. Black holes remain the crucibles where speculation meets accounting. The page curve, entropy rising, then falling for an evaporating hole, now appears in semi-classical calculations that incorporate quantum extremal surfaces. Islands form in the entanglement wedge of the radiation, signaling that degrees of freedom once thought interior are, for the purposes of bookkeeping, already outside when enough radiation has been gathered. The picture points toward non-local encodings that preserve causality and unitarity, while demoting the horizon's naively classical separations. Complementarity returns in modern costume. No single description covers all observers at once, but no observer meets a contradiction. Firewalls are avoided not by denial, but by careful ledgers that account for entanglement without duplication. Whether a complete microphysical story will name the bits strings, loops, qubits on a code, or something stranger, remains open. The rules it must satisfy are less open. No superluminal messages, no violated unitarity, no dead experiments. Time acquires new interpreters in this choir. In relational programs, one subsystem plays clock while others evolve against its readings. The universe's becoming is a pattern of correlations, not a metaparameter floating outside. In holographic tailies, computational complexity grows long after entanglement saturates, mirroring the expansion of black hole interiors and suggesting that an arrow of time may be codified in the difficulty of revering history. Thermodynamics ties arrows to entropy, complexity ties them to effort. A speculative unity peeks through. The felt flow may be the interface-level summary of many monotonic quantities, entropy, typicality, complexity, that cannot all run backward in concert without violating the laws that sculpt them. Across all these proposals runs a stern requirement: preserve every verified decimal place while opening a space for new ones. Quantum networks that perform loophole-free Bell tests, atomic clocks that disagree across stair steps, gravitational wave ringdowns that parse no-hair theorems, horizon images that measure photon rings, surveys that map baryon acoustic oscillations and weak-lensing shears. These are not invitations to overwrite but to constrain. Any theory that reinscribes reality must let these facts reappear as approximations in domains where they were born, the way classical mechanics emerges from quantum theory, as a limit and general relativity yields Newton's law at weak fields and low speeds. Speculation is permitted to replace furniture. It is not permitted to move the walls. A theme consolidates. When disparate roots, strings and loops, amplitudes and tensors, decoherence and collapse, agree on a moral, attention is owed. The shared moral is not the name of a fundamental constituent but a grammar. Relations over things, invariance over appearances, information as currency, geometry as ledger. Whether spacetime is woven from qubits or indexed by spins, whether dark energy is a constant or a field, whether the wave function is an object or an instrument, The program that will succeed is the one that makes the translations exact where they should be and graceful where they can be. Reality, in this mature sense, is not a list of parts but a consistency among descriptions, each faithful on its own domain and stitched together by symmetries and limits. Thus theories and speculations do not multiply worlds so much as compress them into a single, more demanding world. In that world, entanglement can be distance, a boundary can be a bulk, a polytope can be a scattering, a horizon can be an entropy, a clock can be a field. The wager is that the same sentence, written in different alphabets, will read as the universe. The test will be severe. A prediction found at the edge where instruments almost fail, a paradox dissolved without collateral damage, a bridge built that carries both geometry's weight and information's cargo. Until then, theory stands like scaffolding around a cathedral not yet revealed, measuring, aligning, ensuring that when the tarp falls, the structure that appears will hold under every sky. The apparatus of the present age resembles a fleet leaving harbor at dusk, instruments slipping into different bands of reality, each tuned to a distinct register of the same score. Their purpose is disciplined and singular, to test whether geometry can be read off from information, whether quantum correlations carve the shape seen by gravity, and whether the layered portrait of the world holds when pressed by precision. Timekeeping leads because time bears the smallest seams. Optical lattice clocks, strontium or ytterbium atoms frozen in light-standing waves, stabilize their ticks to parts in 1018. A single ion clock, a lone ion in a radio frequency cradle, adds a second voice of comparable purity. Compared across fiber links in free space, such clocks map Earth's gravitational potential like surveyors tracing isobars. Raise one by a few centimeters and its frequency slides, a local confession that relativity is not a romance but a restraint. Networks of clocks promise chronometric geodesy, where time becomes the geodetic datum and the planet's slow breathing, groundwater shifting, volcanoes swelling, is measured as tempo rather than height. In the same breath, clock comparisons look for drifts in fundamental constants that would betray ultralight dark matter brushing through, or a subtle fifth force threading the familiar. Quantum tests reveal how correlations are written in the world. Loophole-free Bell experiments pin detectors kilometers apart, choose settings with cosmic photons or fast electronics, and close every historical escape. The inequalities fall, confirming that separability was never the right axiom. Satellite platforms distribute entanglement over continents, demonstrate quantum key distribution in orbit, and teleport photonic states across space. The feats do not send messages faster than light, yet they turn non-local structure into a working resource. Matter wave interferometers widen the palette. Cold atoms in fountain-like trajectories split and recombine, their phases recording gravity's tug, Earth's rotation, and the faintest whiff of passing fields. Ambitious instruments, MAGIS, AION, MIGA, aim at longer baselines where ultralight dark matter and low-frequency gravitational waves might stain the fringes. Proposals to witness gravity-mediating entanglement between tiny masses point toward a tabletop cross-examination of two pillars. If two objects become entangled only via their mutual gravity, then gravity must carry quantum degrees of freedom or mimic them with impossible dexterity. Where gravity shouts, interferometers listen. Arm lengths of 4 kilometers become rulers for spacetime's flex. Black holes merge in distant darkness, and the pattern of their chirps matches equations first written with chalk. With catalogs of events, strong field tests sharpen. The rate at which a ringing remnant forgets its distortions, the polarization and speed of the waves, any dispersion that would hint at massive gravitons, all are hunted in the data's harmonics. This ground-based band will be joined by a spaceborne ear, an array in heliocentric orbit, millions of kilometers on a side, will open the millihertz sky where supermassive black holes court and collide. Third-generation instruments on Earth, tunnels longer and quieter, promise reach to the earliest binaries and the precision to dissect ringtones into spectroscopic lines of geometry. A complementary ear tunes to years, not seconds. Pulsar timing arrays, global networks of millisecond pulsars used as galactic clocks, measure the slight, correlated drifts in pulse arrival times caused by gravitational waves with wavelengths the size of light years. The signature emerging in cross-correlated timing residuals is consistent with a stochastic background, perhaps the distant murmur of many supermassive binaries or a fossil of early universe processes. If resolved, individual sources could become baselines for strong field tests at truly colossal masses. If the background spectrum deviates from astrophysical expectations, the anomaly would point toward physics that predated light. Horizons are made visible by assembling the planet into a telescope. Very long baseline interferometry at millimeter wavelengths stitches dishes into an aperture the size of Earth and resolves the photon ring around black holes. The diameter and asymmetry of the ring test the spacetime around a compact mass. Polarization maps sketch magnetic fields near the brink. As baselines multiply and shorter wavelengths become practical, the image sharpens toward a movie. Orbital hot spots, lens encaustics, and variability tracing plasma dynamics in curved geometry. An upgraded array, with more stations and broader bandwidth, aims to turn silhouettes into diagnostics. Small deviations in ring structure could signal alternatives to the Kerr metric, while multi-frequency imaging disentangles plasma from metric and pushes the question: does classical geometry fully describe the exterior? Against the very line where quantum bookkeeping must begin. Cosmology provides the ledger's largest pages. Surveys map galaxies by the millions, measure baryon acoustic oscillations as a standard ruler, and track redshift space distortions to read the growth rate of structure. Weak lensing, the shearing of galaxy shapes by foreground mass, draws gravitational fields without luminous tracers and tests whether gravity's law bends on cosmic scales. Space missions widen and steady the view, delivering infrared imaging and spectroscopy that reach deeper in time and minimize atmospheric nuisance. The cosmic microwave background, observed in temperature and polarization at ever finer angular scales, constrains the baryon density, the total matter fraction, the curvature of space, and the scattering history of the first atoms. Lensing of the background reveals the integrated mass power along the line of sight. A curl pattern B modes in polarization would whisper of primordial gravitational waves and fix the energy scale of the earliest instants. New instruments, large multiplexed cameras on high, dry plateaus, satellite missions for polarization purity, aim at this faint script, the kind only seen by eyes grown impossibly patient. The Hubble tension and its cousins are turned from headlines into diagnostics by these campaigns. Distance ladders that begin with Cepheids and tip of the red giant branch stars yield an expansion rate somewhat higher than inferences drawn from the pristine sky under the standard cosmological model. Structure growth appears modestly slower than early universe fits suggest. Whether these dissonances are calibration scars or windows into new physics, the tools are designed to discriminate. Time delay distances from strongly lensed quasars, standard sirens from gravitational wave sources with electromagnetic counterparts, redshift drift over decades, and cross-correlations that weave independent probes together to cancel systematics. If a crack exists, it will be located not by a single measurement, but by a geometry of constraints closing on one point. Particles and forces, meanwhile, are interrogated for portals to hidden sectors. Xenon and argon time projection chambers weigh silences underground, hunting for the delicate taps of weakly interacting massive particles. Resonant cavities and Josephson junction haloscopes listen for axions converting into microwaves inside strong magnetic fields. Small, ultra-clean calorimeters seek light-dark matter recoils. Beam dump experiments and fixed target runs search for dark photons and other feeble messengers. The Large Hadron Collider, operating as a precision factory, scrutinizes the Higgs boson's couplings and self-interaction for deviations that would betray new fields, while flavor experiments test rare decays where heavy virtual actors can leave imprints. If no unmistakable signal appears, upper limits form a pen around theory, forcing ideas about symmetry, naturalness, and the vacuum to write within tighter grammar. Neutrino instruments weigh ghosts. Long baseline experiments watch beams change flavor across nations. Gigantic water and liquid argon detectors catch faint flashes and track cascades. A spectrometer in Germany counts electron energies at the end of tritium's decay, pushing down direct bounds on the neutrino mass scale. Antarctic ice and radio arrays listen for neutrinos crossing the planet, opening windows to cosmic accelerators and testing Lorentz invariants at extremes. Cosmology provides a complementary decree. Heavier neutrinos suppress small-scale clustering, so maps of the large-scale structure place an upper bound on the sum of masses. Together, these tools map a parameter space that will not only complete the standard model's ledger, but also influence how the early universe processed fluctuations into the architecture seen today. Short-range gravity and symmetry tests address the foundations with stubborn simplicity. Torsion balances hunt composition-dependent accelerations that would signal a fifth force. Satellite missions drop test masses together to parts in 1015, looking for differential free fall. Atom interferometry checks the universality of free fall for quantum matter waves. Clocks test Lorentz invariants by searching for sidereal variations in frequency ratios as Earth rotates and orbits. Gamma-ray bursts and blazar flares, observed across energies and distances, constrain energy-dependent speed of light variations. Polarization from distant galaxies limits birefringence in vacuum. Null results are not disappointments here. They are walls that shape the corridor toward a viable theory of spacetime at small scales. Quantum simulators stand as rehearsals for problems the universe does not stage for observers. Cold atoms in programmable arrays mimic lattice gauge theories. Superconducting qubits implement unitary circuits whose entanglement growth and scrambling can be timed. Analog black hole horizons appear in flowing condensates, generating phonons with a spectrum suggestive of Hawking's logic. These tabletop analog gravities cannot arbitrate the deep questions alone, but they test universal mechanisms: how chaos spreads, how information scrambles and then recoheres under echo protocols, how entanglement saturates area laws before complexity continues to climb. If spacetime is an error-correcting code, these are the benches on which hardware learns the very tricks geometry seems to know. The sky's newest eye, infrared, cold, and sharp, unfurls structure in the early universe with a clarity unimagined a decade ago. Strong lenses multiply distant galaxies and quasars into time-delay laboratories. Reionization's patchwork becomes visible as galaxies ignite their neighborhoods. Metal lines track how the first generations of stars seeded complexity. These details are not decoration. They are constraints on how quickly the universe built entropy gradients and structure from a smooth beginning, constraints that flow back into models of inflation and dark matter. Future telescopes on the ground, mirrors the size of houses, will measure the slow redshift drift, the secular change in cosmic redshift over decades, a direct kinematic probe of expansion that bypasses standard candles and rulers. Across these domains, the instruments share a philosophy: measure invariants and relations rather than objects. Standard sirens rely on the amplitude, frequency relation set by general relativity. Weak lensing measures correlations in shapes. Bow measures a comoving scale imprinted as a relational fossil. Clock comparisons measure frequency ratios. Bell tests measure correlations between outcomes, not hidden trajectories. Reality, interrogated this way, is asked to produce the same answer when seen from many angles. If spacetime is emergent from information, the emergent metric must still deliver the ring size around a black hole, the Shapiro delay of a radio pulse as it grazes a mass, the spectrum of a kilonova's R-process glow. If quantum correlations underwrite locality, Their patterns must still respect causal order and forbid messages that outrun light. The tests are not invitations to dream. They are requirements to wake ideas early and see if they stand. What arrives next is not a revolution by proclamation, but by convergence. Next-generation gravitational wave observatories will convert rare events into routine weather and parse the ringdom of heavy remnants into multipole lines where deviations cannot hide. A spaceborne interferometer will listen to the choir of supermassive binaries and perhaps to lighter relics, cosmic strings, phase transitions that vibrate in the millihertz. Telescope arrays will turn horizon silhouettes into movies and read polarization to separate plasma's handwriting from geometry. Sky surveys will measure cosmic acceleration with multiple rulers and clocks, strong lenses and sirens, drifting redshifts and lensing shears, while simulations connect these observables with baryons, feedback, and nonlinearity. Quantum networks will extend entanglement beyond city scales, probing foundational questions with space as a partner rather than a barrier. Clock networks will become continental instruments that hear the planet and the passing of fields. Matter wave interferometers will either see hints of new ultralight sectors or silence those rumors with authority. In this mesh of tools, the criterion for success is austere. A satisfactory grammar of reality must reduce to general relativity in the infrared with all tested symmetries intact, reproduce the statistics of quantum experiments including Bell violations and contextuality, conserve information across horizons without inventing faster-than-light couriers, and account for the cosmos's measured expansion while either explaining or honestly quarantining the smallness of vacuum energy. The instruments described are the gatekeepers of that grammar. They do not dictate which story must be told, but they mark where any story will be rejected. Thus, ongoing testing is not a background hum. It is the metronome by which theory must keep time. The clocks, interferometers, telescope arrays, and underground halls are not separate empires. They are one observatory whose domes face different horizons of the same sky. If spacetime is a ledger of information, these are the auditors. If information is the weaver of geometry, these are the looms on which consistency must appear as pattern. What they will deliver is not merely more data, but a narrowing corridor. A corridor that, if followed faithfully, should open not into a smaller room but into a single, higher chamber, where the layered portrait reads as one image and the word real names exactly what remains when every test has been applied. When the ledger of measurements is set aside and the room grows quiet, the question returns without theatrics. What in the grammar of physics deserves the name real? The layered portrait, classical appearance resting on relativistic geometry, both leaning on quantum substrate, has not dissolved the world into metaphor. It has moved the center of gravity. Reality looks less like a census of objects than a concord among descriptions, a web of invariants that survive translation from one frame to another, from one scale to the next. In that concord, a pattern begins to show. Symmetry speaks first, not as ornament but as law. Invariance under a shift in time ties itself to energy's conservation. Invariance under a slide in space binds momentum. Invariance under a rotation secures angular momentum. More abstract symmetries protect charges and stitch fields together. These are not preferences of equations but fixed points that maps must share. The stage can be recast, coordinates stretched, clocks compared at different heights, observers boosted into motion. Yet the conserved quantities remain, like the melody that persists when orchestration changes. In this view, the real is what stays the same when the world is legitimately redescribed. A stone's position is parochial. The statement that momentum is conserved is cosmopolitan. The block of spacetime, drawn by relativity with an almost cruel calm, widens the lens. Past and future do not grace the manifold differently. Events arrange themselves into a four-dimensional order in which now is an indexical, not a universal. Yet within this block, arrows appear. their shafts carved by boundary conditions and dynamics rather than by metaphysical decree. Entropy increases along time-like curves as records accumulate and gradients flatten. Stars burn hydrogen into heavier ash and leak negentropy into cold space. Structure forms and dissolves. Biological systems harvest free energy to maintain low-entropy intricacy for a while. Time's flow, so fiercely felt by the mind, may be the interior rendering of monotone functions that cannot be reversed without extraordinary conspiracy. Entropy, typicality, computational complexity. The block remains. Becoming is written into it as a pattern of asymmetries, a one-way embroidery stitched from an improbable beginning. If that embroidery is law-like, the human aperture is not. Biology equips minds with a narrow bandpass, wavelengths that happen to thread water and air, timescales suited to heartbeat and gait, lengths tailored to hand and tool. Instruments widen the window. Radio dishes make the galaxy audible. Cryogenic detectors hear the tap of neutrinos. Interferometers notice that space has shrugged in a galaxy far away. Still, the act of noticing is never innocent. Choices of basis, of coarse graining, of what to condition on, all of these are part of the experiment. The triumph of physics is not to escape perspective, but to make statements that all perspectives must honor. That is why invariants matter. They strip away the parochial and leave behind what no honest observer can disagree about. In this sense, reality is what refuses to be edited out when apparatus and assumptions change. The quantum state, written as a wave function or as a vector in a more austere space, resists a single metaphysical badge. Some treat it as an instrument encoding expectations about future records, others as a field of potential, ontic and complete, others as a catalog of consistent stories that no single observer can hold at once. Decoherence, branching, collapse, each offers a scaffold on which outcomes become definite in practice. Each honors the ledgers of experiment to uncanny precision. What unites them, beyond polemics, is a shift in emphasis from objects to relations. Whether or not the state is real, as a substance, its measurable content is relational, probabilities for joint outcomes, phases that matter only between alternatives, entropies that count correlations rather than volumes. The ontology may remain contested. The operational core is not. The world answers to joint questions with a structure that cannot be mimicked by classical assignments of pre-existing properties. The difference is not semantics. It is the hard residue left by Bell tests and interference and the stability of macroscopic records. Geometry, too, seems to ask for a demotion that is also an exaltation. If entanglement patterns can be read as areas, if minimal surfaces in a higher dimensional bulk compute the entropy of boundary regions, if error-correcting codes make spacetime resilient by storing information redundantly, then distance becomes a derived measure of how hard it is to recover information across a cut. Curvature becomes the way correlations arrange themselves when coarse-grained. None of this turns geometry into an illusion. It offers a reason for geometry's authority. The metric may be emergent, but it is not negotiable. It arises because many microdescriptions agree, because only certain patterns of correlation can stay consistent under renormalization, because horizons count in bits written on their skins. What is real, then, is the necessity of this ledger. The impossibility of a world that maintains its recorded facts without shaping them into a geometry recognizable as spacetime in the domains already tested. At horizons, philosophy is forced to show its receipts. If information is preserved, then the division between inside and outside cannot be the simple one classical geometry suggests. If no drama greets an infalling observer, then the smoothness promised by relativity must coexist with encodings that an exterior observer can use. Complementarity, one description per vantage, no contradictions when vantages meet, sounds like tact until calculations enforce it. The page curve traced by modern semi-classical techniques suggests that the world is neither sentimental about locality nor careless with unitarity. It keeps books in ways that no single narrative voices completely. That multiplicity is not a failure of reality. It is a rule about how reality can be known. In this landscape, mathematics does not merely describe, it selects. Structures that admit dual description, that keep conservation laws intact while allowing different faces, rise to the top. The suspicion that the universe is mathematics can be read modestly. Whenever a structure is rich enough that its theorems match facts across many domains, and whenever measurements keep returning invariants that the structure protects, the distinction between the math of the world and the world blurs. Still, contact with experiment is the adjudicator. Beauty is a guide with a record, helpful, not sovereign. The status of the vacuum remains a standing challenge to taste. If zero-point energies conspire to nearly cancel, some symmetry or mechanism must be named. If they do not, and the smallness is anthropic across a landscape of vacua, then explanation migrates to statistics and selection. Either route revises what counts as enough in an account of reality. The first adds a principle the equations have not yet revealed. The second accepts that typicality over a larger ensemble can explain why a particular patch looks the way it does. Both readings demand the same discipline. No claim should survive that cannot reproduce the sky's spectrum, the web's growth, the siren's amplitude, distance relation, the ring's diameter around a black hole. Reality's entrance exam is cumulative. If time has a double life, static in geometry, arrowed in history, so does meaning. On one face, reality is what persists, symmetries, conservation laws, relational counts. On another, reality is what resists, anomalies that survive calibration, paradoxes that cannot be dismissed, small but consistent tensions that demand theory move. Both faces are necessary. Without persistence, there is no law. Without resistance, there is no progress. The shock of non-local correlations, the insult of a vacuum energy that will not play fair, the discipline of ringtones that match predictions to many decimals. All of these are not separate mysteries, but facets of one. A world whose most stable features are written in invariants, and whose most puzzling ones mark the limits of current translation between layers. Humility follows naturally, not as posture but as method. Maps succeed precisely because they remember where they fail. Approximations work because they carry error bars like epaulets. Classical mechanics has not been falsified by quantum theory, it has been situated. General relativity has not been weakened by quantum arguments, it has been bracketed. Quantum mechanics has not been softened by decoherence. It has acquired a domain of rhetoric where ordinary language can describe what records are, and how they come to be without pretending that superpositions cease to exist. The ethic is not to overthrow but to embed. Reality, if it is a single story, will be a story in which every correct earlier chapter remains legible in the right light. The human place in this story is not central and not negligible. Minds arise as local defeats of entropy, engines that build models to harvest work from structure and then return their heat to the night. Those models are never the world. They are reconstructions that succeed to the extent that they capture invariants and respect constraints. Meaning, purpose, value. These are not quantities a telescope can plot. They are emergent in the same way that temperature is emergent, real at the scale where they function, not available to a question asked with the wrong vocabulary. The philosophical caution is not to mistake emergence for illusion. A storm is emergent and real. So is a melody. So is a promise kept. If geometry can be real and emergent from entanglement, then so can meaning be real and emergent from neural and social entanglements. Nothing in physics forbids this. The forbiddance comes only from category error. What remains unanswered is not small. What microscopic degrees of freedom weave spacetime? How do they count information at horizons and release it? Why was the early universe so smooth that complexity could grow an arrow? Is acceleration the voice of empty space or of a field still moving? Do parameters sit where they are by symmetry, by dynamics, or by typicality in a larger ensemble? Does the wave function describe the world or the world as seen by agents? And is that a false dichotomy? The list is long, but each entry has been paid for by data. None is a vanity. The closing image, then, is not a curtain but an aperture. A laboratory at night, two optical clocks disagreeing by a whisper over a stair, a radio array listening to the dying ring of a merger many galaxies away, a cryostat where a qubit's phase processes and a record is born, a dish that collects photons last scattered when the first atoms formed, a chalkboard where a minimal surface finds a partner region whose entropy it measures. On the same planet, ocean and wind trade heat, trees lift water against gravity with sunlight's help, cities pulse with work bought by gradients the cosmos will eventually erase. Above, the sky is not silent. It is old, still writing. If reality must be named, let it be named this way. It is the intersection of all faithful descriptions, the invariants that persist across frames, the relations without which records would contradict, the grammar that lets clocks, fields, and observers keep one another honest. In that grammar, objects are the nouns tradition prefers. Symmetries and entanglement are the syntax that makes sense possible. Whether the stage is fundamental or emergent, whether the code is quantum bits or something stranger still, the requirement remains austere. The story must read the same under every honest light, and the layers must slot without squeal. Until that grammar is complete, the measured world is already enough. A ledger that balances to many decimals, a chorus of instruments that agree, a set of paradoxes that point like compass needles trembling toward a pole not yet charted.